All right, so we're gonna get last couple ones here, and again, these ones are more, to me, more of a fun physiology than these are really physiologic adaptation. It's kind of some certain weird environmental physiology things. I mean, in reality, there is adaptation with some of the space ones here, uh, but one of the ones that's always kind of interesting is deep sea diving and some of the physiology that comes along with that one. So this is one. If we have time at the end, a lot of times I'll try to throw this in there just as a way to kind of fill a little bit, but also to expose everybody to some just kind of some interesting physiology and some of the weird things that go along with it. So when we talk about deep sea diving or we talk about scuba diving, one of the things that you need to know is water being, we've talked about it with temperature, but water is much denser. Because of this, when you start going under depth in water, you start having a lot more pressure around you. Uh, in order for this to not collapse your body, we have to put air in at higher pressure to keep these inflated. So what this does is it means that there's a lot higher alveolar gas pressure. So if you remember the partial pressure, these are going to be much higher when it comes to actually dealing with breathing pressured gases. And what we can see is beyond certain limits, this can become very dangerous for the body. And some of the physiology, like I said, is really kind of interesting. So the main thing it kind of comes down to is at sea level you'd be under 1 atmosphere, but when you start going into water, because it's so much denser, it's about every 33 feet or about every 10 meters is going to be another atmosphere. So when you start going down to 100 feet of water depth, you're really looking at you're being under 4 atmospheres of pressure, and you can see how this starts building up really quickly. And again, you get down to 300 feet underwater, that is 10 atmospheres of pressure that is on the body. So again, starts being really kind of a big deal. And a lot of these gas laws we've talked about before end up being kind of a big deal as well. So if we start talking about volume and pressure, that is a linear thing. The greater the pressure, the smaller the volume. So what that means, if you're breathing a gas at depth, let's say you're at 100 feet, compared to sea level, you're going to have that gas 3 times the amount of gas in the same volume. And that can be a big deal if you're going from depth up. And this kind of shows that idea right here. 1 liter of gas at sea level would be at 33 feet, would be half a liter. It'd be 1/8 of a liter at 300 feet underwater. I mean, at 233 feet underwater. So you can see very quickly these volumes get compressed. One of the things that's kind of interesting with this, and this becomes an interesting thing for a couple reasons, but to actually supply these gases to the lungs, you have to deliver the stuff at much higher pressure. As you start doing these higher and higher partial pressures, something that generally isn't an issue for us can become much more of an issue at pressure. So nitrogen is the main gas here we're going to see for a couple reasons, one of which is nitrogen narcosis. So if you're going to be underwater for a long period of time, you're breathing compressed air, which is going to be, let's say, I mean, even if you're only at 33 feet, that's another atmosphere. Once you start getting down a little bit deeper, we can start seeing what is called nitrogen narcosis. This is starts seeing it after about an hour at 120 feet of depth. To start with, you kind of act a little drunk. Little euphoria, stuff like that. As you start getting deeper, drowsy. Really, when people start getting down to these greater depths, and this is part of the reason generally you're not going to be doing scuba at these depths, at 200 to 300 feet, but you really start getting almost clumsy, like you're really, really drunk. Greater than 8.5 atmospheres, really your ability to do anything is minimal. You are so euphoric and kind of wasted on nitrogen that you're going to be risking death if you stay down at these levels. So a lot of times they call this rapture of the deep. The main thing is what happens is this nitrogen at these higher levels gets into fatty substances, and the big issue becomes getting into neuronal cell membranes. It alters ion conduction, it alters our ability to send action potentials and a lot of that, and reduces neuronal excitability, so it acts as a depressant, much like alcohol. And again, at high enough levels, this can be very, very dangerous. And this kind of shows you kind of these different atmospheres. At 2 to 4 atmospheres, mild euphoria. You start getting 4 to 6, calculation errors. You can't control the fact that you're just laughing. Sleepiness as you get deeper. Dizziness. Hysterical laughter. And you can see in some of these ones, stupefaction, which is just a fun word in general. And as you start getting deeper, you can have hallucinations and unconsciousness. You can lose consciousness due to this. So again, shows you one of the reasons that these pressurized gases are something you really need to pay attention to. The other thing we have to watch out for is at these high levels of pressure, we can start having issues with oxygen poisoning. When you get really high oxygen alveolar pressures here, you can actually start getting brain seizures. So really, when you start getting oxygen at above 4 atmospheres of pressure, this can cause issues if you're down there too long. And again, like it says here, can occur without warning in certain people and can be deadly to these folks that are at this depth if they're submerged. And again, this is just kind of showing you the normal partial pressures at sea level 760. But that's partial pressure in the lungs, not in the environment. You can start seeing here's your normal oxygen level right here, normal alveolar pressure. You can see once you start getting above those, this green line here is really talking about how much dissolved in the water of the blood, which is not normal with the oxygen hemoglobin. It's usually all in hemoglobin, only 1%. As we start getting greater and greater amounts of this in here, that is going to lead into this oxygen poisoning. And again, dizziness, nausea, disorientation. Anything that you're doing is more active is going to even increase this, more so than somebody who's just breathing and moving slightly underwater. So it can kind of give you that idea that as you get at these higher levels, it can become an issue. And this is also where, as you start getting into some of these greater depths, this is where some of these oxygen and air mixtures of gases you're breathing tend to change as you're at greater depths. Generally, only down to about 150 feet do they do oxygen, not oxygen, but normal pressurized atmospheric gases. At that point, we start messing with these mixes and doing things like heliox and trimix, these different kind of combinations of gases that are going to help deal with either the nitrogen narcosis, the oxygen toxicity, maybe doing a little bit less in this one here, so you're not pushing too high of a partial pressure in on these gases. The other thing that's an issue here is our body deals with free radicals pretty well in the body at normal atmospheric pressures. If you start getting too high of partial pressures here, we can start overwhelming some of these these systems that are in place to oxidize free radicals. So as long as that buffering system is fine at normal partial pressure of oxygen, we generally can take care of it. Above a certain amount, it's generally about 2 atmospheres, we can start getting greater amounts of free radicals and can start having some damage to these cells. And again, nervous tissue, because of its high lipid content, is much more at risk to this. And even after you bring people back up, they are going to be at a greater risk for oxygen poisoning after they've been at depth. Generally, carbon dioxide poisoning is not an issue. Really, when you're doing pressurized gases, you're really not getting carbon dioxide at high enough levels to be an issue. We're generally also exhaling this off as it's formed, so it usually doesn't become an issue. So as long as we're keeping carbon dioxide levels at normal values on the inhaled gases, we're usually fine. Where this can become an issue is some of these ones that are trying to not have as big a tank or try not to give off bubbles. So we do have certain rebreathing apparatuses, especially with military diving, that is going to try to not generate bubbles. And you're going to be rebreathing more gases. So once we get about to twice normal levels of the alveoli, we start having some issues with respiratory depression. They can start to begin to fail. We start having issues with respiratory acidosis. If this gets too high, can cause you to lose consciousness. Nitrogen, like I said, normally not an issue, but when we get into really deep levels here, we can have issues with this dark nitrogen narcosis. The other issue here is it gets carried everywhere in the body. When we start getting into these higher levels, again, at these higher pressures, it's really that increased atmospheric pressure that is keeping most of this in solution. Nitrogen, unlike oxygen, CO2, it is not metabolized at all, so it gets dissolved in these tissues. When the lung level gets lower, we can reverse this and get it going back out of the tissues, back to the lungs. But the thing is, this takes a long time for us to breathe these gases back out. If you do this too fast, you can get decompression sickness. So at sea level, 1 liter of nitrogen is dissolved, like it says there, in the body. We don't get a lot of that dissolved in the water here. Again, much more soluble in fat as it is in water. So as we start getting in greater depths, we're going to have more and more liters of nitrogen dissolved in the body. The main problem with this one is for these gases to reach equilibrium, it needs to take some time. We can reach equilibrium with breathing, but it takes time to breathe this off. So again, it's not going to reach equilibrium super rapidly, and even after you come to the surface, it's going to take some time. And it's again only after hours that we can get some time on this one. The other thing is, if you're at several hours at deep levels, you're going to reach equilibrium with this nitrogen, and you're going to have a lot of it dissolved in the body. If you're only down there for a few minutes, not much nitrogen dissolves into the tissues. So it's really a balancing act of how long you're down there versus how long it's going to take you to come back up. But the main thing is if you have been down there long enough, you're going to have large amounts of nitrogen in the body. If you come back up too fast, what can happen is with breathing, you can't reach equilibrium fast enough, and you're more like a soda bottle has a bunch of carbon dioxide in it, but in this case nitrogen, and if you come up too quick, nitrogen bubbles, due to that lack of pressure, can come out of solution in your blood, in your tissues, and minor to serious damage can occur depending on how much. It's really how big are these bubbles, and that is going to be a lot of times what's referred to as the bends. So when you're at compression, you are going to have this really high levels of oxygen and nitrogen in your system. If you remove it too fast, you all of a sudden have nothing holding this in solution, and this much greater levels of this in the tissues that are all going to now try to come out of solution. So the bends a lot of times is these gas bubbles coming out of solution. And again, these bubbles can block really small vessels a lot of times into bigger and bigger vessels. Generally, you start feeling pain in the joints and the muscles of the legs and arms, and that's where they kind of talk about this being the bends. It hurts really badly. If this gets to be too much going in here, you can start having issues where not enough oxygen getting to the brain. You can also get blocking of the blood vessels going into the lungs, which can lead you to not being able to get blood to the capillaries of the lungs, and this is referred to as the chokes. So you're trying to gas for air because you have this shortness of breath. This can be deadly if it's bad enough. Generally, what you need to do is bring this person to the surface slowly. This nitrogen, and that can be expired through the lungs and prevent decompression sickness. And like you say here, if you're down there and you've really been saturated, 2/3 of the nitrogen will be liberated in about an hour. It takes about 90% in 6 hours. And generally, they have tables about how long you've been at depth and how long it should be coming up to do the safe decompression. But if you go down to, if you're breathing scuba gases and you're down at 190 feet, this is the decompression schedule. So as you're rising back up, you need to stop and take about 10 minutes at 50 foot of depth. As you get up to 40 feet of depth, you need to take another 17 minutes, and you can see it's up to almost 2+ hours in that 20 to 10 foot depth. What this really means is it's very difficult to carry enough breathing gases to really go down to this 200 foot of depth because the amount of time you need to spend decompressing. So for only an hour on the bottom, you're doing 3 hours of decompression on the way back up. And again, this is why generally scuba diving, generally people are working under 100 feet. You're not usually going down super deep on these ones. It's usually 20, 30 feet, maybe 60, 80 feet, but anything after that, you start getting to having some issues with the amount of time you can spend there and really how long it takes you to reach equilibrium on the way back up. You can put a diver into a decompression tank and then slowly bring atmosphere back up to normal. This is a lot of times used for people with decompression sickness, so you can slowly put them quickly back under pressure and then slowly relieve the pressure. And then if there's any issues, you can put them back down to that deeper pressure and then bring that decompression over a slower period of time to try to keep them safe. A lot of times these are also used for people doing work at really great depths. Divers sometimes working at really deep depths, so 250 to 1,000 feet. A lot of times they will have them going into a tank, and that tank can stay pressurized. They can bring them back to the surface, but keep them under pressure. And the main thing is once you're at saturation levels, there's really not much changing. So as long as you maintain that pressure on the person, there's not any major issues. But once you start the decompression process, it's going to take quite a long time for them to get back to sea level pressures. So as long as you keep these saturated at the levels that they're going to be to when they're actually in the water, they're safe. I mean, obviously there's some issues with narcosis and some of these other things are depending on the gases that they're breathing. A lot of times they're not using nitrogen gases, they're using something called Helios, which is Heliox, excuse me, which is, Helios is a running shoe, sorry. Heliox is actually that breathing gas that is a helium-oxygen mixture, which tends to help people not have issues with nitrogen narcosis. But as long as they're kept at this depth, they can keep going at that pressure and coming back into this tank without any issues. Like I said, generally diving at these deeper ones, they're going to use helium instead of nitrogen. It is way less narcotic on the body. And because of that, the other thing is only about half as much helium dissolves into the body tissues as nitrogen, and generally tends to come back out a lot easier compared to nitrogen. Also, again, makes this a lot easier to breathe. It's a less dense gas. When you start really pressurizing this gas and going to these really high levels of depth, the airway resistance with this super dense gases, these super high pressure gases, starts to become an issue, making breathing almost impossible to do when you start getting to these greater depths. That the airway resistance becomes so much because you have so much nitrogen in this, so much pressurized nitrogen in this, it becomes almost like a thicker air to breathe. So that's another thing that these helium does. One of the things it does have an issue with is you lose more body heat to helium. It is not very thermally insulating. So if you're doing a lot of breathing in a cold environment of these heliox gas, it can cause drops in core temperature. So that is something that needs to be paid attention to when somebody's working at this. Another thing that, like I said too, is when you start getting these great depths, generally you're going to start reducing the amount of oxygen below atmospheric levels in that mixture. So when you're pressurizing this up, you're similar to pressurized levels. They do this a little bit with space because you're trying to do a less pressurized suit. They do like 3 times the oxygen at 1/3 the pressure in like a space suit. So you're still getting sea level oxygen, but at a different pressure. So they do kind of the opposite thing when we're at deep sea. They start reducing the levels of oxygen in there. So like it says there, at a depth of 700 feet, that'd be 22 atmospheres of pressure. You're only going to want about a 1% oxygen mixture because that is going to get you about normal atmospheric levels of oxygen. So if you have 22 times the pressure, or 21 times the pressure, and you're at 1%, normal pressurized gas, normal oxygen is about 21% of the mixture. So they will start reducing that oxygen level to get rid of any of these issues with oxygen toxicity. Like it says there, at 4 atmospheres, a 21% mixture of oxygen is likely to cause seizures within 30 minutes. So again, you got to start tweaking what gases you're breathing as you go deeper, because the issues with oxygen toxicity and nitrogen narcosis really mean you have to start playing around with what breathing gases you're doing. If you did buy the textbook I talked about, it does have a little chapter on this, and it goes through a lot of these different gases and what you breathe at different depths. It's really kind of interesting. Scuba is that self-containing breathing apparatus. When you're doing this one, you're generally doing normal air. Takes these high pressures, reduce them to a lower level, and generally the valve, what it's doing with the demand valve is it's kind of realizing what the pressure is there and really tweaking that regulator to the point that that little bit when you would take a breath in is enough to let these gases come in. And generally you don't want a lot of dead space on any of these things here, because that is going to increase your work of breathing. So, like it says here, the reducing valve takes the pressure that's in the tank and puts it to only a few millimeters above that surrounding water pressure. So when you do that inspiration, that slightly negative pressure is enough to open up the diaphragm of the mask and release the air into the lungs. And again, then on expiration, we blow this gas back out into the sea, so we don't have issues with, like I said, carbon dioxide at all. Like I said, going to these depths, so when you're doing these pressurized normal gases, it's really very dangerous. You can only spend a few minutes at 200-foot depths before you have to start coming back up, due to how the tissues get saturated, as well as the amount of gases that you can bring, because it requires a lot of pressure to be able to do that there. And like it says, that airflow of the tanks that's required to get the carbon dioxide out of the lungs. The greater pressure means you have not a lot of time at these gases before you need to start heading back up to depressurize. Another thing that's interesting, and I always like talking about this one in A&P, but you can escape from submarines as deep as 300 feet without any breathing apparatus. You generally need some type of breathing apparatus when you're at deeper than that. But the big issue becomes is when it's kind of the opposite of what we talked about. When you have that pressure on that, at 300 feet, you're at about 10 atmospheres. What this really means is the air you breathed in, if you were to come up to sea level, is going to expand 10 times over. So if you were to hold your breath and try to go up from a submarine, the air in your lungs is going to expand to 10 times its volume. It will burst blood vessels, it will burst alveoli. When a person is coming up from this depth, they almost have to continually exhale. And it's really because of the fact that those gases that were under pressure at the 300 feet of pressure are now expanding greatly. And if you don't, you will rupture different body tissues. So again, really weird physiology that a lot of times you don't think of normally that you see at this depth is really kind of interesting.